So work converts one kind of energy to another kind of energy. And we learned that we can use an applied force to do work on something to create kinetic energy. We can also create potential energy, right? If I lift up a boulder, I'm doing work on the boulder, and I create potential energy. And so it's important for us to recognize when our work is going to create kinetic energy and when it's going to create potential energy. And we'll cover a couple of different things in here: gravitational potential energy and power, and spring potential energy. So we'll start with gravitational potential energy. We found how we had last time a definition for kinetic energy. The definition for gravitational potential energy is defined as mgh, delta H. And that delta H is the only thing that's tricky about this, right? Mass is pretty straightforward. G is always going to be negative 9.8. The delta H means that you're talking about potential energy in relation to some origin where you have set the level to 0. Okay, so if I'm like in a normal situation and I'm, say, lifting a rock like this fella here, I would set the y equals 0 to be the ground level, and then I would define delta H to be from there to there. But it's important and a little confusing um, to recognize that that H is arbitrarily defined, right? So if I defined the potential energy of this rock relative to the center of the Earth, it would be much higher than if I defined it relative to this. Okay, so the energy in that system depends on our coordinate system. It doesn't change the results we get. Oftentimes we're choosing our y equals 0 in order to make the problem easier. But it does seem sort of impossible, right? How do I change the energy just by picking a different y? And the answer is that potential energy is always defined as a relative thing. It's not an absolute amount of energy. If you think about it, neither is kinetic energy, right? Because kinetic energy, we're using a reference frame. And in different reference frames, an object has different amounts of energy or different amounts of velocity. That means that that kinetic energy is also in regards to a reference frame. But don't worry about that too much. Most of the time, it's going to be pretty easy to figure out what your y equals 0 is. If we check the units of this, and you could go ahead and do that, you would find that they are the energies of, or the units of energy, right? Because we've got a kilograms times m over second squared times that second length unit. Okay, nothing here defines a path or distance, right? It doesn't matter how this rock gets from here to there. He could lift it straight up, or he could lift it and carry it over here and back over here and then get it to here. It's going to have the same amount of potential energy relative to the ground. And that means that this force is path independent. What that means is we don't care how it gets from point A to point B. All right. So let's talk about kinetic energy and the work energy principle. We have a cuckoo clock here, and if you ever used a wound clock like this, what you do is you pull this little key down, and it pulls a weight. So this might be made of lead or iron or something. So it gets pulled up here, and then slowly that gravitational potential energy is converted into the energy needed to turn the clock until the acorn gets back down here, and then you have to go in and pull it back up to keep the clock going. Okay, so when you do work on the chain, you might ask yourself, why doesn't it add kinetic energy to this chain weight system, right? If work is the work equals the change in kinetic energy, you'd think that when I did this work, force in the direction of distance, that I would be adding kinetic energy here. But instead, the acorn is stopped up at the top. Well, the answer to that is network, right? We need to think about network. The network here is the work of my applied force um, essentially minus the work of gravity, right? Because this acorn is still moving this upward direction. Gravity is moving downward direction. So we have that cosine 180 there. And so the gravitational work is opposing the applied work. That's why it's, heavy to pull it up. What that means in terms of potential energy is that when you do negative work against a conservative force like gravity, that's when you add potential energy. Okay, so the gravity here is doing negative work on this acorn. And whatever we've added through that negative work becomes the potential energy, the gravitational potential energy of that lead weight. Okay, so we do applied work. Gravity does negative work, and that gravity doing negative work is what adds gravitational potential energy. Okay, so then we can talk about spring potential energy. In an ideal spring, and we talked about this with force, the spring is proportional to displacement, and that's Hooke's law, right? We even saw this video before, or this, this little image before. I can extend it or I can push it in. The farther I push it in, the more force it's going to apply. So what does that mean in terms of energy? Well, if my force changes with distance, that means when I first start pushing that spring in, it's going to be easy to push. And then it's going to get harder to push and harder to push and harder to push, right? Until I get to my XF. And then the force here is much higher than it was before. Okay, so it's not as simple as gravity, right? Gravity is going to be the same no matter how far if I lift something from 0 to 10 feet, the forces are going to be the same as I lift it from 90 to 100 feet, right? But that's not true here, okay? The force increases as we displace something. We can define the work as the force times the distance. And when we plot that out, what that means is the potential energy. The work is the multiple of FD. F is our y-axis. X is our x-axis. In that case where we're multiplying the y and x-axis, we want to look for the area under the curve. Just like when we look at a velocity plot, right? And we want to find how far you've traveled, right? If this were a velocity plot, I'd multiply t on the x-axis times v here. I'd want to find the area under that velocity curve to find the distance traveled. This is the exact same mathematical thing. Okay. So this guy becomes a nice way of explaining our average force, right? Because we can look at this triangle and figure out our average force. And then we know what our average force is, and we're going to multiply that by distance, right? So our average force is here, and it already has a d in it, right? We're going to multiply it by d, and so we're going to get a squared term. And that means the potential energy of a spring is the displaced distance squared times that spring constant times a half. And notice it looks a lot like our velocity kinetic energy equation. So this here is a plot of potential energy for displacement. If I displace my spring this much, I've got this much kinetic energy or potential energy. If I displace it 2 units instead, I've got more potential energy.